You sit down to write a simple Python script. The goal is straightforward. Create and store a basic profile for a new student. Look at this code editor. We have written exactly 3 lines of logic that define a name, an age, and an output command to display the data. You hit run, expecting a clean output terminal to appear. But instead, the script immediately and violently crashes, freezing the whole system. To a human reader, that logic makes perfect sense. We know Alex is the first student, and they are 20 years old. But Python completely rejects it, blocking the execution with a wall of syntax error and name error alerts. To understand why this fails, we have to look at how Python handles a concept called a variable. A variable is essentially a strict contract used to store data in a program's memory. This contract relies on the assignment operator, the equal sign. Its exact job is to bind a human-readable identifier on the left side to a specific value stored in memory on the right side. If you do not follow Python's exact naming laws for those left-side identifiers, the machine simply refuses to execute. That makes mastering syntax and learning to debug your code the most critical survival skills for any coder. We must run a forensic autopsy on our broken script, zooming in on the first line of code to see exactly why it failed. Python enforces a strict rule for variable names. They can contain letters, numbers, and underscores, but never start with a number. By taking that numerical digit and moving it to the back, we create a compliant variable name. Next, we move our investigation down to the second broken line of code, where we tried to define the student's age. This error triggers because of a secondary syntax rule regarding what Python calls reserved keywords. Foundational keywords like if, for, and true are structural pillars of Python. You cannot use them as custom variable names because Python owns them for core operations. We fix this by swapping the keyword true for a legal identifier, renaming it to age equals 20. These rigid rules exist to maintain strict order. They guarantee that the Python interpreter never confuses the custom data labels you invent with the internal commands it needs to run the machine. With the definitions repaired, we hit the final fatal error in the script, the name error triggered by our output command. Python is ruthlessly case-sensitive. A memory box labeled lowercase myvar is completely isolated from one written with a capital M or all caps. When our script prints the misspelled variable name, the system scans memory, finds no exact match, aborts, and returns a flashing name error. We resolve the crash by fixing the typo, ensuring the print command asks for the exact, perfect spelling of the variable we defined. Now that the names on the left side of the equal sign are legally defined, we can look at the right side to see what data is actually populating those fixed variables. Using Python's type function, we can inspect our data. We are storing 2 foundational data types in this script, a string for the text characters in Alex and an integer for the whole number 20. If we added a decimal, we'd store a float. A functioning variable requires both components, a perfect legal identifier on the left side, properly bound to a valid recognizable data type on the right. Back in our code editor, we can view the fully repaired script. The variables are now completely legally compliant. We execute the corrected code. This time it runs flawlessly, successfully pulling the data from memory and outputting the student profile. These naming rules provide the bridge for translating human intent into machine execution. Understanding these constraints allows you to stop guessing at syntax and start writing code that the interpreter can predict and execute every time. By mastering variables, strict case sensitivity, and reserved keywords, you acquire the exact vocabulary required to build complex systems in Python without crashing.